Hello, I am Subhi Barg, an assistant professor at Mid Sweden University. Today, I will talk about one important subject that is related to the design of magnetic components. Recently, I have seen a shared post in LinkedIn that is about the core optimizer, the magnetic core optimizer of Frenetics. And that tool is designed by Frenetic company, which is a startup company that design magnetic component. So the post is shared by Anish. So I will share my screen first. As I have said, 2 days ago, I have seen this post from Anish. And the post is the following. Post 19 from Anish, Frenetic AI Core Optimizer. So this optimizer, it uses AI as it is claimed by Frenetic, but we'll verify this. So Anish has used this tool to optimize an LLC transformer, a transformer for LLC converter. We will look to the design steps of that he shared. But before that, I will just give you the plan for this meeting. So first, we will go through the results, optimization results of Anish that he got using the core optimizer of Frenetic. Then I will discuss the video of Professor Ben Yaakov, in which he has unfolded my teaching about the fake inductor. So this is the two principal parts that I will discuss today. So let's start by the first part that is related to Frenetic Core Optimizer. I have commented in my LinkedIn. I have posted this post in which I said that the approach used by Frenetic is fundamentally wrong, and today I will explain why. And also I will discuss the results of the number of turns, the optimal number of turns given by Frenetic Core Optimizer. So here what I said that it's very basic that B and N are interdependent through Faraday's law. So the core optimizer, the principle or the main idea of the core optimizer can be understood from the shared file by Anish. So as you can see here in this file, it seems that the user has to give some input first. And this input is the magnetic flux density, the peak magnetic flux density. And then the user has to choose different cores and different materials. And then what the core optimizer will do, it will change the number of turns, and then do some calculation of core loss and winding loss, and then do some optimization, and it will give you the optimal number of turns and the optimal core, and finally the optimal solution in general. I doubt about the other results shared by Anish. So we can follow the design step given by Anish. So step number 1, he tested different magnetic core, PQ32, ETD34, EC35, and all using 3C90 material under 250 millitesla. So this approach is fundamentally wrong because you cannot test the same different cores using the same magnetic flux density. That's incorrect. So this is the fundamental mistake of this core optimizer. The second step, he tried to choose the best material, of course, using this tool. So it seems that, or the result shows that 3C95 is the best material, as it has the least number of turns, 20 turns for 3C95, however, 30 turns for 3C90. You can notice that there is a big difference in the number of turns between these two materials. Based on my experience, this is not true. And today, I will show you how to verify this. So let's start first by explaining the optimization process for magnetic component. So here the idea is to determine the optimal number of turns and then determine the minimum losses for that, which will give the minimum losses, in fact. So we have first to determine the equation for core loss and winding loss. Core loss, they are given by Steinmetz equation, given as follow. Here, K is dependent on the magnetic material. It is a Steinmetz parameter. Alpha and beta also, they are called Steinmetz parameters, and they depend on the material also. Here, this frequency, which is the switching frequency, and B max is the maximum magnetic flux density. And here VC, it's the core volume, which is equal to the core cross-section multiplied by the core length. This is for the core losses. But if you want to determine the optimal number of turns, then these core losses should be expressed as function of the number of turns. We can get this through Faraday's law, which is given as follow. It's function of the number of turns, the core cross-section, the frequency, and the magnetic flux density. So here the number of turns times the core cross-section times the frequency and times P max. And K1 here, it's just a factor that includes the effect of the waveform, the shape of the waveform, voltage waveform, and also there is a factor of 2 here in Bmax. Normally we should find 2 Bmax. That's delta B. So it is included all in K1 because they are all constant. They will not affect the optimization process. So here then, Bmax, it's equal to the voltage divided by K1 and AC and F. So it could be expressed as a constant K2 divided by the number of turns. And K2, it's basically the voltage divided by K1 AC and the frequency and the frequency. So we have to replace the equation of Bmax in equation number 1 here for core loss. And what we will find, PC as function of the number of turns. It's equal to a constant, I will denote it K3 times 1 over n to the power of beta. And K3, it's equal to K times F to the power of alpha times the volume and multiplied by K2, which is function of the voltage and the core cross-section and the frequency, but should be K2 to the power of beta also. So that one is K3. You can do some simplification because here VC is also function of AC and K2 is also function of AC. So you can do some alteration to this equation. But since it will not affect, the optimization process, we'll keep it as K3. The second fundamental equation for the optimization is the winding losses. So I will note PW, and the winding losses, they are function of the number of turns. They are equal to the number of turns times the resistance of one turn times the current squared. This is the fundamental equation for computing the winding losses. So I can note this term as a constant because the current, it's basically constant for a given power, and the resistance also for one turn, it is for a given core, it is also constant. So I can note it K4 times the number of turns. In order to determine the optimal number of turns, we need to calculate the derivative of the total losses with respect to the number of turns. The total losses is the sum of core losses as function of n plus PW as function of n. We replace, this is equation number 2, and this equation number 1. So 1 plus 2 is equal to K3. This is 1 basically also after modification. K3 times n to the power of minus beta plus K4 times n. And in order to calculate the optimal number of turns, we need to calculate the derivative of that equation and equate to 0. So will be the derivative with respect to n of K3 n to minus beta plus K4 n. And this one, it will give you minus K3 beta n to the power of minus beta minus 1 plus K4. This should be equal to 0. Now solving this equation will give you here n to the power of minus beta minus 1, it's equal to K4 divided by K3 beta. This is the equation. This is the expression for n to the power of minus beta minus 1. And then the optimal n, the equation of the optimal n is K4 divided by K3 beta to the power of 1 minus beta plus 1. Okay, this is the final equation to be considered for an opt. Now, we need to understand this equation. So K3 here, it includes the magnetic material that comes the Steinmetz parameters K that we have defined in our first equation and multiplied by other terms, which depends on the specification of your application, the converter. That's the voltage, the frequency, and also you have alpha as the Steinmetz parameters. That alpha depends on the material, okay? And this K4, it is only just about the conductor specification. So it has not any dependence on the magnetic material or the magnetic core. And beta, it's the Steinmetz parameters of your magnetic material. So the results that has been shared by Anish, it shows that for 3C95, he found 20 turns, and for 3C90, he found 30 turns. So N opt for 3C90 5 is equal to 20 turns, and N opt of 3C90 it's equal to 30 turns. This is optimization results given by Frenetic Core Optimizer. So we can verify this. So the difference here, or we can calculate the ratio, an opt of 3C90 divided by an opt of 3C95 is equal to 30 divided by 20. And that's, is, we can calculate this. It's equal to 1.5. So the number of turns is 1.5 higher for 3C90 than that found for 3C95. That's a big difference, more than 50%. Okay, now how we can verify this? We can calculate the ratio of between these two materials using this equation. Okay, now I can copy this equation in your page. So an opt, it is found K4 divided by K3 beta to the power of 1 divided minus beta plus 1. So if we divide this for the two materials, then we can find the ratio also. But before that, we need to understand the loss ratio between the two materials. Loss ratio of 3C90 divided by the losses of 3C95. We need to get an idea about this two material, the loss ratio between these two materials. So here I have the data sheet of these two materials, so we can see them. Just I have to bring it now. Okay, here we have it. Sorry. Yes. No. Yes, here we have it. So the first material, 3C90, we can read the data sheet. For example, for 100 degrees Celsius, 100 kilohertz, 200 millitesla, we have 450 kilowatt per cubic meter. And for 3C95, we have, for the same test condition, we have 290. So if you divide 450 by 290, we'll find 290, we'll find 1.55. So it's 1.5 times higher than the losses of 3C95. Of course, we can also do more verification by considering also the effect of the temperature. Maybe 100 degrees Celsius is not suitable. We can look to the typical working temperature in power electronics, which is around 80 degrees Celsius. And we can also consider 100 kilohertz and 200 millitesla. So for 3C95, you can see here the losses, they are approaching 400. I think it's around 370. You can read it here. We can do the same for 3C90, and you can look for 80 degrees Celsius. It's about, it's higher than 400, but it's less than 500. I think it's around 470. So if we divide 470 by 370, we find 1.27. So that, if we use the data in the first table, it will give 1.55. But if you use the data here, it's 1.27. So I think the data given in the table here could be considered as the worst case. So I'll consider this one, even that it is smaller in reality. So we'll consider this results should be equal to 1.5, 1.55. Okay, now we need to remind something about the Steinmetz equation. So the Steinmetz equation, it's given by this equation, k times f exponent alpha to the power of alpha, b to the power of beta, and times the volume. So here both material have the same magnetic core. So you don't need to look to the volume right now. But let's understand this equation, because these parameters, beta, alpha, and k, they depend on the magnetic material. So it will be a problem here if we make this, we divide this for two different materials. But for a given frequency and a given B and a given temperature, this equation could be written as follow for both materials. So PC1 for 3C95 or 3C90 could be written as K1 times F to the power of alpha 1 and B to the power of beta 1. We can do the curve fitting for PC2 for 3C95, and this will be equal to K2 times F alpha 1. We can get the same thing, alpha 1 and B to the power of beta 1. Yes, we can do for a given test condition, frequency, and B and temperature. You will get the same. The only difference is these parameters. And K1 divided by K2, which I will not, it's equal to KR, the ratio between the two different, it's equal, should be equal to 1.55. And that's the worst case. So KR for other test condition, it will be smaller than this one, because we have verified, we have approximated this, and we have seen that is for a real application, this ratio it's smaller, because this one KR is equal to K1 over K2. It's basically, it's PC1 divided by PC2, since alpha 1 and beta 1, they are same for both material. You can do it without any problem, and you can get the same very accurate result. So now we have found out that both material have same alpha, same beta, but different K. So now let's compute the ratio. We have to find out where is K in the equation of an opt here. So K, it's here in K3. We can remind you where is K3. It is this one. So K3, it's K times F to the power of alpha times VC times K2 to the power of beta. So alpha, they are the same. The core, it is same. Beta, it's same. K2 also, it is same, because that's the voltage waveform factor. And here, the only difference is this K. We have K1 for 3C90 and K2 for 3C95. So all this term, if we divide the ratio n opt for 3C95, 3C90 divided by n opt for 3C95, all this K4 and beta and the remaining factors in K3 except for K will be cancelled out. So what we'll get at the end, so at the end for the n opt for 3C90, it will be 1 over K1 to the power of 1 divided by minus beta plus 1 and divided by 1 to the of K2 here for n opt for 3C95 to the power of 1 over minus beta plus 1. Okay, so we can compute this. Okay, so beta, it is same for both material. So this equation, it is like you have parameter a to the power of x divided by b to the power of x. So you can just write a divided by b to the power of x. Okay, so what's this will give you? It will give you K2 divided by K1 to the power of 1 over minus beta plus 1. Okay, this is the ratio between the optimal number of turns for both material. Now K2 over K1, I can bring this here. So it will be equal to Kr to the power of 1 over beta plus 1. Okay, so this one, it's equal to 1 over Kr or to the power of 1 beta plus 1. Now we can compute this factor. So I can use MATLAB here, but you can do also the calculation for yourself. So it is 1 divided by Kr, it's 1.55 to the power of 1 over beta plus 1. Now we need to understand beta, the effect of beta, this equation, 1 over beta plus 1. So 1 over beta plus 1, it's a decreasing function. So if I increase b, beta, the function will decrease. And if I reduce beta, the function will increase. So this term will also increase if beta is decreasing, and the whole term, it will decrease. So here we should take the worst case. Maybe I can put beta normally, it is varying between 2 and 3, but 3 is, you cannot find any material with beta equal to 3. Usually it's less than 2.5. So maybe the worst case could be considered as 2.5 for beta. So here I can replace, it is the whole, the ratio of the number of turns, the optimal number of turns, it is equal to 1 over 1.5 to the power of 1, 3.5. So let's see what we get. So 1 over 1.5 to the power of 1 over 3.5. we get 0.8. So here we got 0.8. We can try it also for a beta equal to 2, because in principle we should get a ratio that is bigger than 1. So let's try it for beta equal to 2, because the optimal number of turns for 3C90 should be a bit higher than 3C95, because it has higher core losses, 3C90 compared to 3C95. So I think the problem here, it is in beta. So let's try for beta equal to 2 and see what we get. So instead of 2.5, I will get only 2. So we will get 3 here. Here I got 0.86 also for beta equal to 2. So maybe I need to verify this minus. So here we have an opt 3C90 divided by an opt 3C95. And this is 1 over minus beta plus 1. Okay, I got what's the problem. So here, KR, it's K1 over K2, it's 1.55, but here we got 1 over KR, sorry. This one is 1 over KR. This should be 1 over KR, and this should be 1 over KR. That's why. So one over 1.5. So I will get 1 instead of 0.8. I will get 1.13. So you see, it's very far from 1.5, that 1.13. I can also test it for beta equal to 2. So here I got 1.15. For beta equal to 2, I will get 1. But also, I think I can share MATLAB here with you and maybe upload as function of beta to see this term, how it varies. So here, I think I can put beta as a variable varying from 2, 0, 0, 1, step of 2, 3. And then my equation, it's 1 over 1.55 to the power of 1 over 1 over beta plus 1. Yes, this is the equation. I can plot this to see the whole evolution of this function, or the ratio of the optimal number of terms. So as function of beta and y. This y is n opt, the ratio of n opt. So let's see. Some here should be. So here I can show you I think I made also a mistake here. Let me check the equation, the correct equation. Okay, so the whole should be 1 over. This equation should be 1 over this. Of course, you can simplify the equation. Some practices, I think. Here. Okay, here I can show you now. So you can see that the optimal number of turns, the ratio of the optimal number of turns between any materials, considered any material. It can vary between 1.11 and 1.15. And this for beta varying between 2 and 3. Okay, maybe the loss ratio here between both material, I considered it only 1.50, 1.5 times. That's it. So the loss of 3C90, it's only 1.5 times bigger than 3C95. Okay, let's consider maybe, for example, not 1.5. Let's see 2 times. And let's see what we get. So 2 times you will get the maximum. If beta is equal to 2, you will get 1.26 times. But usually beta is around 2.2, 2.3, so you get 1.2, around 1.2. That's the losses, they are 2 times bigger. So very far from 1.5 that they got. 30 divided by 20, that's 1.5. Too far. You know what does it mean, this? Now we can go back. So if it is, we find the loss, an opt of 3C 95 or 3C90 divided by an opt 3C90 5, it's around 1.15. What does it mean? If we consider the number of turns of 3C95 is correct result, 20 turns, then an opt for 3C90 should be 20 times 1.15. That's, okay, maybe we do calculation here. 20 times 1.15. That's 23. So this is very far, 23 turns. So you see, what does it mean, this 23? It means complete wrong results for the optimization. Why? You have 7 turns difference between the real optimal and the results given by Frenetic Core optimizer. So if it is 30 turns instead of 23, that means higher winding losses. And this, when you try to build your transformer, that 7 turns, that additional 7 turns could lead to one more layer. And if you increase by one more layer, then the AC resistance, it will increase exponentially. If you look to Dowell equation that calculates the AC resistance, you will see the effect of the number of layers. If you increase the number of layers, the winding losses, the AC resistance will increase exponentially, and the winding losses will do so. And this will lead to increase the temperature of your transformer. So this is not the optimal solution that is given by Frenetic Core Optimizer. So I think I have finished now with today. I hope that you will learn from this how to optimize and how to verify the results when you use uh, tools, optimization tool from companies. So the engineer should be careful where he get his knowledge, and he should be careful which optimization tool he has to use. Nowadays, we have so many optimization tools that available in the web, available in the internet, and most of people they use it without knowing what's the advantages and disadvantages of these tools. I personally don't use any of these tools. I only design my optimization code and do my optimization. And usually I get results much better than what is available now in the internet. So you can see also in the internet, Frenetic Optimization Core, it is supported and endorsed by so many experts. People, they are there are so many people who looks like they are expert in magnetic design, but we can see here we have verified together that this tool it does not give the right and the correct answer or the correct solution. So I hope that today you learn a little about the optimization of magnetic components. Thank you very much for attending and for watching this video, and I hope to see you in a future video.